Today we're going to study the capacitance of a conductor. It's a circuit property just like resistance and inductance. Consider an arbitrary shaped isolated conductor. If we give Q amount of charge to this conductor, then it will gain a potential V. If we increase the amount of charge on this conductor, the potential is going to increase proportionally. If we double the amount of charge, the potential is going to double. If we triple the amount of charge, the potential is going to triple. Such that the ratio Q by V remains a constant. And this constant is called the capacitance of the conductor. Okay? It's just the proportionality constant. When you convert this proportionality into an equation, Q is equal to C times V, then you find that C can be defined as Q divided by V. The capacitance of a conductor is just the ratio of the charge on the conductor to the potential. Now this constant becomes independent of both Q and V. Why? Because if you increase the charge, the potential increases proportionally, but the ratio, which is the capacitance, remains constant. Okay, what does this constant depend on? We have found that this capacitance depends on the size and shape of the conductor and the nature of the medium surrounding the conductor. Both of these dependencies we will see in a short while. But before that, we'll talk about the SI unit of capacitance. The SI unit of capacitance is a farad, represented by an F, capital F. 1 farad is defined as the ratio of 1 coulomb charge per 1 volt. So we'll say 1 farad is equal to 1 coulomb per volt. What it basically means is that if you have a conductor and you give 1 coulomb of charge to this conductor, the potential, if the potential of the conductor raises to 1 volt, then that conductor will have a capacitance of 1 farad. You will see again in a short while that farad is an extremely large unit. Not a practical one. Why? We'll know soon. First, we'll calculate the capacitance of some regular shaped conductors. Let's first find the capacitance of a conducting sphere of radius r. Consider a sphere of radius r, a conducting sphere of radius r. Let us give Q amount of charge to this sphere. Then this sphere will gain a potential given by kq divided by r. So therefore, the capacitance can be found by the formula Q by V. So C is equal to Q divided by KQ divided by R. This Q and Q cancels out. You have R divided by K. So here you can see clearly that the capacitance depends on two things. R is the radius. This radius is the representative of the size of the conductor. And K is the Coulomb's constant. And we know from earlier classes that this Coulomb's constant depends on the nature of the medium. Now, if you have a vacuum surrounding the sphere, then you could write K as 1 by 4 pi epsilon naught. So the capacitance of the sphere in vacuum would then be 4 pi epsilon naught times R. Okay, see clearly from this result that the capacitance is independent of the amount of charge that we have given to the sphere and the voltage that it has gained. But the capacitance depends on the radius. This is the size of the conductor. And 4 pi epsilon naught is something that represents the vacuum surrounding the sphere. Okay. Now, I'll show you from this formula that why is 1 farad a very large unit. Now, if you imagine a sphere of certain radius that has a capacitance of 1 farad, what would be the radius? So let's calculate what is the radius of the conducting sphere that has a capacitance of 1 farad. So we know the capacitance of a sphere is now given by this formula, that is R divided by K. So R is equal to K times C. So we want to find out what's the radius of that sphere, which gives a capacitance of 1 farad. 1 farad is 1 coulomb per volt times K. K is the Coulomb's constant. And if you assume the medium surrounding the sphere as vacuum, then K has a value of 9 into 10 to the power of 9 volt meter per coulomb. You see, coulomb cancels out, volt and volt cancels out, and we are left with 9 into 10 to the power of 9 meters. That's an extremely large radius for a conducting sphere. It's about 9 into 10 to the power of 6 kilometers. Way larger than the radius of Earth. If you see how much larger it's than the radius of Earth, if you divide 9 exponential 6, if you divide this number by the radius of Earth, which is 6,400 kilometers. So what number do we get? This is approximately 1,400 times the radius of Earth. Such a large sphere is not practical. You cannot have such a large conductor. Okay, so there's one more question that we can take up here, is that if we assume Earth to be a conducting sphere, what would be its capacitance? Okay, so how do we find the capacitance? We know now that the capacitance of a spherical capacitor is 4 pi epsilon naught times R. So for Earth, R is 6.4 into 10 to the power of 6 meters, which is 6,400 kilometers. And if you substitute it here, so C is equal to, this is by the way 1 by K, and that is equal to 9 into 10 to the power of 9. So sorry, this is in the denominator. R by K, this is 6.4 10 to the power of 6 divided by K, that is 9 into 10 to the power of 9. Okay, if you solve this, you will get approximately 711 into 10 to the power of minus 6 farads, which is 711 microfarads. See, such a large conductor such as that of an earth, spherical conductor such as that of an earth, only has a capacitance of 711 microfarads. Okay, so typically you would not see practically the capacitances in farads. You will see the capacitance in the units, typical units of capacitances are maybe microfarads. It's a very large capacitor, by the way, nanofarads and picofarads. You know what a microfarad is? 10 to the power of minus 6 farads. Nano means 10 to the power of minus 9 farads, and a pico is a 10 to the power of minus 12 farad. Okay. Ideally, we want the capacitance to have a very large value. But to get a large capacitance, you need a very large conductor, which is not practically possible. So engineers and scientists have found out a solution for that. What's the solution? That if instead of one conductor, you take two conductors separated by a small distance by a dielectric medium. Here I have drawn two arbitrary shaped conductors, and each conductor is called a plate. And in between them is a dielectric medium. Now, if we give equal and opposite charges to the two conductors, then effectively what we are doing is we are reducing the potential difference between the two conductors. And if the potential difference is reduced, the capacitance gets increased. So what charges we give? We say we give, this is the conductor that we give plus Q charge, and we bring another conductor near this conductor having an equal but opposite charge, minus Q. Okay, this way the potential difference between these two conductors decreases and the capacitance increases. And we can achieve, for very small set of conductors, we could achieve a very large capacitance. Okay, and thus this arrangement is called a capacitor. So capacitor is a device that consists of two conductors called plates separated by a dielectric medium. Okay, we'll see later that greater the dielectric constant of the medium, greater will be the capacitance of the capacitor. Okay, so we have achieved a very large capacitance using small conductors separated by a dielectric medium. We take those conductors nearby and keep a dielectric medium having a very large dielectric constant in between the conductors, thus achieving a appreciable amount of capacitance, which can be used for various purposes. Okay. Now the point is, how do we give an equal amount of charge to the other conductor? Suppose this is one conductor having a charge Q, a positive charge Q, and we bring another conductor. Now we call that conductor a plate, near it, not touching it, and we want to give an equal amount of charge to this plate. So there are two ways. One is through induction. You bring it near it and connect it to the ground. Once you connect it to the ground, you will see that it will gain an equal amount of charge, but opposite in sign. Okay, this is one way. Another way is you connect the two conductors, the two uncharged conductors, to a battery. Okay, one pole of the battery to one conductor and another pole of the battery to the other conductor. Clearly, this positive pole of the battery pulls out electrons from this conductor, thus giving it a certain plus Q amount of charge, and those electrons flow towards this conductor and giving it a minus Q amount of charge. Okay, then later on we disconnect this. Okay, so we get an arrangement of two conductors having the opposite polarity, okay, of charge. There is of course a potential difference that is now attained, and that potential difference is not represented by ideally we should have written the potential of the positive plate as V plus and the potential of the negative plate as V minus, so that the potential difference between them would have been V plus minus V minus. But we represent this thing, this entire thing, the potential difference, we continue to represent it with V, the potential. So the potential difference actually is represented here with V. So thus capacitance is defined in this case as the charge given to one of the plates. We usually take the positive plate divided by the potential difference between the two plates. This is how we define the capacitance now. Okay. In the next video, we'll be discussing the various types of capacitors. The classification of capacitor is based upon capacitors are classified on two things. One is the shape of plates, and the second is the medium between the plates. So based upon shape, we have three types of capacitors that we have to do. First is the parallel plate capacitor. The second we have to do is a spherical capacitor, and the third we'll be doing is the cylindrical capacitor. And based on the medium, we'll have a capacitor with dielectrics and capacitors without dielectrics. First, capacitors, all types of capacitor shapes, capacitors without dielectric, and those that have dielectrics, with various types of dielectrics. Like we have dielectric medium, we could be a paper, so we have a paper capacitor. Okay, Dielectric medium could be mica, so we have a mica capacitor. It could be some kind of electrolyte, so we have electrolytic capacitors. Various types of capacitors that we will discuss, but all this in the coming lectures. Okay, thank you.